Hello, this video is going to demonstrate the numerically controlled oscillator working in hardware. So real quick, I'm just going to run through how it's programmed. So we are going to start here at the frequency to delta phase part of the module. This is going to take some user-defined frequency, multiply it by this number here, and it will generate the change in phase. So for a given frequency for the oscillator, you have to divide that by the frequency of the system clock to get the actual change in phase of the sine wave that we're trying to produce. So instead of actually doing the division, we're just going to use fixed point multiplication by a large fraction. And so you can see that I have this 40-bit number represented in Q2020. So there's 20 integer bits and then 20 fractional bits. And then I'm multiplying that by our user-defined frequency, which is 24 bits wide. The first 21 bits are going to be integer bits, and then the last 3 will be fractional bits, and then we essentially concatenate it with 16 more fractional bits that aren't going to be definable by the user. They'll be hard-coded. Right now, the actual frequency is hard-coded just because there's no way to control the frequency at this stage in development. So if I want to change the frequency, I have to enter the number and then recompile and reprogram. So after the delta phase is calculated, that's going to tell us how much we want to move up in the sine wave. And so it'll be added on to the current phase value of the sine wave, or like the time value, if you will. But that phase is actually used as an address for a lookup table. See, we convert it to this or we assign it to the PAC address, or the phase to amplitude converter address. And this is just a huge lookup table. It's going to take a 12-bit address and output the 12-bit amplitude of a sine wave. And so then we assign that to the wave out output. That's a 12-bit output. But then I'm going one step further just for development purposes and taking the MSB, which is essentially the sine bit of the output wave. And so that sine bit should change twice every cycle. So it'll basically look like a square wave that has the frequency of our oscillator, or whatever the user set the frequency to. So I've dubbed it the NCO clock out. I've then assigned this pin to one of the GPIO pins on the board. It's actually right here. And I've got this reading into my oscilloscope. It's a tiny little thing. And essentially I've programmed this right now to have its frequency at 1024 hertz. And as you can see on here, our square wave is about 1025. I think there's some rounding errors going on, and that'll be a bit tricky to work out whether that's the oscilloscope's problem, because it's rather cheap, and it's going off visually how this looks, and then if it's actually just my programming, because this is a bit tricky math here. So the number here is figured by taking the amount of integer bits of our frequency and then dividing that by the system clock. And that gets us that decimal number. And converting that to binary, of course, is a bit difficult. You can't get as accurate as you want, but this is as close as I was able to get. So for right now, it will take some more analysis to see how accurate the NCO is actually at this moment. But then after that, or at least along with that, what I want to do is hook this up to the DAC. Because right now, the 12-bit output of our NCO isn't something we can visibly see. We can't see the sine wave yet. And as development goes on, when we start doing actual modulation, we want to be able to see the behavior of the wave. It won't look like a sine wave anymore. The sine bit might change quite a lot. And so what we want to do is hook it up to the DAC to get an analog output and to analyze that instead. So at this stage, now that we're sort of getting the sine wave, the pure sine wave worked out, that'll give us a good foundation for designing and validating the connection to the DAC. So how that might go is we would have some sort of master controller, which already has plenty of responsibilities with regards to the system. It would essentially read the output of our NCO over SPI and then pass that output to the DAC over SPI. In general, what I'm going to have to do is develop some sort of SPI interface in the FPGA itself, because I don't think there's one built in here. And if there is, that would be nice, but I don't think that's the case. I will look into that, actually. I think there might be. There's an ADC that's on this board, and some of the pinouts have been labeled SDA and SDC or something like that, SDA and SDO, or I don't know, whatever. Anyway, I think that is a good, basically, overview of the current system and where I plan to go with regards with the DAC. So let me know what you think. Thanks.